right? So pressure at state 1 is simply atmospheric pressure, PATM, right? Pressure due to the atmosphere, or 1 ATM, or 1.013 times 10 to the 5th pascals. The way we measure pressure due to the liquid, in this case it's water, it's the force of water pushing down divided by the cross-sectional area. So what is the force of water? The force of water happens to be due to the column of water that's above you. So that column is simply the weight of water above you per cross-sectional area, except mass can be written in terms of density of the solution times volume of the solution times gravity divided by the cross-sectional area. But the volume of fluid above us is that column of fluid above us that I've drawn, right? The cylinder or column of fluid above you. So in that case, the volume can be written as the last fraction. So density of water times volume of water times gravity. This is mass, right? Because we know density is equal to mass over volume. I just multiplied the volume over to find the mass. Does that make sense? And then divide by cross-sectional area still. I'm just still using the same equation. I'm just expanding on it. And then volume is simply the cross-section times the height or the depth of that column times gravity divided by the cross-sectional area. So you notice that the cross-sectional areas cancel out, and the pressure due to water is simply the density of the fluid medium that we're in times gravity times how far we're below that medium. Because realistically, what we're measuring when we're measuring what we call hydrostatic pressure, this is what we call hydrostatic. So stationary water pressure, or commonly referred to as gauge pressure, because that's what you get when you put it next to a gauge and measure it. We call this hydrostatic pressure, or pressure that stays, or water that's staying still, the pressure due to water staying still above us. So it's the column of fluid above you that's pushing down. Weight. W in the FW is for weight, which is why it's mg for the force. And it's the weight of water. So when you say that we have, if you think about it here, if we're standing here on Earth, at the surface of the Earth, we have a column of air above us, and we're measuring that column of air. It's all that density of air above us, and we call that 1 ATM, right? This is also why when we go up higher in elevation, what happens to the pressure when we go up? Say like you go to Denver and you're at like Mile High, or you're at like, Mount Everest. What happens to the pressure? Is it more or less when you're at higher elevation? With our understanding of where pressure comes from now. Less. Good. Why? Because there's less column of gas above you, right? So less air molecules pushing down. And that's how we determine pressure. It's the amount of air molecules pushing down on us at any given point. And it's the weight of all that air, all those air molecules pushing down. Okay? So that's what we determine as hydrostatic or gauge pressure. But to find the pressure at 2, notice I didn't write pressure at 2 yet. Pressure at 2 is what we call total pressure. Total pressure is the atmospheric pressure plus the hydrostatic pressure. right? So it's the column of air above us and the column of water above us that's pushing down. So that's total pressure. So PATM plus rho GH, okay? This is commonly referred to as total pressure. And if you think about it, it makes perfect sense. It's the column of air pushing down on you plus the column of water. Because when you go underwater, you have air above you and you have water above you, okay? Or a liquid above you, right? Does that make sense? Why it's the combined pressures of both of them? Cool. So, so that's hydrostatic pressure and how pressure changes with depth. The other thing that we need to know is that specific gravity commonly referred to is, or commonly used as density all the time, is realistically the density of the object over the density of water at 4 degrees Celsius. Why 4 degrees Celsius? Because that is when water is most dense. Remember, solid water, which is ice, floats above liquid water. So water at 4 degrees Celsius is the most dense water is at any given point. Okay, so specific gravity commonly, usually when they ask you for density all the time, when you have to do density in comparisons in class, you'd look up in the table and compare it to the specific gravity. The reason that you can say that specific gravity is the density of the object that we're looking at or the chemical that we're looking at, it's because the density of water at 4 degrees Celsius is 1 gram per milliliter. Okay, but if it's not in that unit, then it will not be exactly 1-to-1 for specific gravity to density of the object. Okay, so just keep that in mind. So when we talk about density, no, they will not give us the specific gravity of water at 4 degrees Celsius. It's one of those like a priori knowledge things that they expect you to know. And that's just 1 gram per milliliter. Okay, it's not that difficult to remember. So good to know. So now we know hydrostatic pressure, we know total pressure because it's the pressure of gas above us plus the pressure of water above us, okay? The other case is if we don't have an open system, it's not open to the air, and we have a closed system. So we're going to take a look at pressure in a closed fluid system, and in order to do that, we need to know Pascal's principle. So Pascal's principle simply states that the change in pressure at any point of a closed fluid transmits undiminished to all other points. We're not specifically talking, well, technically all of these are things at rest, and then we're going to put a pressure or force on them and get them to move, but still considered technically liquids at rest because it's a closed fluid system. You're only sloshing back and forth between like a closed system. Other points in the fluid. Yeah, so there's 3 things, remember, that I'm going to talk about with liquids at rest. So fluid statics and fluid dynamics. This is the second thing for fluid statics. So a perfect example of this is a hydraulic press, right? For layman's terms, this is a car jack, right? Think of like you pumping up your car and trying to change a tire, right? So on one end, small cross-sectional area, The other end, the large cross-sectional area. Imagine your car is on the large cross-sectional area plate. This is like a piston plate, and then the other end, it's a piston plate. And everything in here is some liquid, and it's closed, okay? So Pascal's principle states that any pressure change at any given point, like the ends, should still be the same at all other points in the fluid, okay? So if we apply a force here over A1, we're going to be able to lift a pretty big force here over A2, right? Be able to lift up your vehicle. So Pascal's principle states that in a closed system, the pressure changes are equal at any point in that fluid. So imagine, since liquids are considered relatively incompressible, if I push one molecule, it's going to bump onto the next one, and transmit that force that I apply to it all the way down to every other liquid molecule, okay? So that's why you can consider the pressure to be the same at any given point, which means what? F1 over A1 is equal to F2 over A2. And to be able to find the force at which we can lift up with, it's simply the ratio of A2 over A1 times the original force at which we apply to the smaller end. And you can see how much force you have to apply to lift up, say, your vehicle, okay? But the key thing here for Pascal's principle is the pressure change is always equal at any given point. Since it's a closed system, we also know that the volumetric change is the same. V1 is equal to V2. So A1 H1 is equal to A2 H2. So this will be your H1. This will be your H2, right? It's going to be fairly small relative to a lot of pumping that you do, right? If you ever had to lift up your vehicle and change a flat on the road. So to find the new height that we can lift this with, it's simply the ratio of A1 to A2 times the original height at which we have. And last but not least, since energy is it's a closed system, the amount of work being done should also be the same. So F1 H1 is equal to F2 H2, which just means that F2 is a much larger force at which we're applying. So in a closed fluid system, all three things apply. You have your change in pressure being the same. Since liquids are incompressible or relatively incompressible, the amount of volume change is the same, and the amount of work done on that liquid is the same when you compare different points along the system. Okay? So one is when it's open, the other one is when it's closed in your system. Any questions so far? Lots of good questions. Why that example? Do you have the page that's on? Oh, I think that sounds like something we should do for office hours, not something that we should do for class, right? Yeah, definitely come to office hours. I can definitely help you guys solve any issues with the book and or examples that you couldn't be able to solve. Oh, but this, okay, if you guys want, we could do this, but I have other questions that I like to ask you guys. I will definitely do this, Iman, during office hours on Thursday, or actually after class today too. We can definitely go over it after class. But yeah, there's other questions I want to get to make sure that I usually ask questions that match up to the topics that I just went over. Okay. So, first question of the day. But yes, using what we just learned, you should be able to answer it correctly. So, for 5.2a. So let's say we have a cannula. Cannula is just a U-tube. By the way, this is how they used to measure blood pressure in the olden days, right? Just a tube. They would stick one end into your arm, usually a vein or artery. There'd be some saline buffer or something, right? We'll call this solution 1. And on the other end, we'll have some solution 2, okay? This is some height B, and then this is some height A. So I want to know someone asked, the book lists many density values in a table. Should we memorize this table? You do not need to remember density values in a table. The only density that you really need to know is water, right? Yeah. I personally don't like to remember anything unnecessary more because there's so much to remember already for the MCAT. I personally like I'll tell you if I find that it was useful, but I generally don't find that useful because I can generally solve for the density of the solution, or they generally give it to you, right? You don't have to remember specific densities for certain solutions. That's crazy. That's too much stuff to remember. I believe the density table, density of water is 1,000 kilograms per cubic meter. The book is meant to be more detailed than what you need to know. That's why we have to pare it down during lecture. But we want to be as thorough when we're giving people to read it, because we have to assume that, it's not everyone's first time taking a course. So this should be a thorough review. But we're going to pare down what we've seen and heard from students on what we should be teaching you guys and what they actually test on the MCAT. Okay. So we'll make it a little bit less scary for those who are saying that the book is like too dense in terms of information. Okay. Hopefully that's better. I don't want you guys getting anxiety from reading questions and the text. So which of the following is not true? A. Solution 1 is less dense than solution 2. B. A column of solution 1 with a height of A plus B has the same mass as a column of solution 2 with a height of B. C. The ratio of density of solution 1 to solution 2 is equal to the ratio of A to B. And last but not least, D, the relative densities could not be determined if one of the sides were closed. So we have solution 1 over here, and we have solution 2 over here. So statement 1. So we're looking for true or false statements. Thank you. It's false statements. Excellent. So, yes, Monica has the right idea. It's good to have a general idea of what's more or less than water, but not exact values. Because you need to know what's like going to float and what's not going to float. And we'll talk about things floating on the third case of static fluidics. Okay. When we talk about Bernoulli's equation, or not Bernoulli's, Archimedes principle. Okay. So we're looking for false statements. Solution 1 is less dense than solution 2. Is that a true or false statement? Looks true, right? Because the green solution is heavier, it's going to push up the yellow solution. Sounds like a true statement to me. So if we're looking at this, we're going to balance the system. We're balancing pressures, right? The pressure on the left has to equal to the pressure on the right. So since both of the sides are open to air, they both have atmospheric pressure, but then this one has density of solution 1 times gravity times the height of A plus B is equal to atmospheric pressure plus density of solution 2 times gravity times the height of B. So since everything is the same below this dashed line here, to the left and to the right, and it's basically the density of it green, we don't really need to know the height of that, right? Because we assume that they should be equal and opposite and they cancel out with each other. But realistically, we're just dividing this cannula in two and doing pressure balance, right? Or realistically, force balance. So we know that the atmospheric pressures will cancel out on either side, right? So they're saying that a column of solution with a height of A plus B has the same mass as a column of solution 2 with a height of B. So density is mass over volume. So we have mass of solution 1 times gravity times A plus B all over the volume, which is cross-sectional area, times that height of A plus B is equal to mass 2 times gravity times B all over cross-sectional area times the solution with the height of B, right? And then A plus B, that's where the A plus B and the B come in, okay? So if we cancel everything out, B cancels out B, gravity cancels out with gravity, A plus B cancels A plus B, and the cross sections cancel out. Are those masses equal? Looks pretty equal to me. So this is a true statement. So the ratio of density, so imagine if we started with this first line, line number 1. If we started there, the ratio of density, so we want to define density of solution 1 over the density of solution 2, right? We'll see that gravities cancel out. And the ratio should be B over A plus B, not A over B. So this is a false statement, right? But for us, that's good because that's the answer we want. Now, for D, sure. I was asked to explain it again. All I did was solve for the ratios. So I wanted to find density of solution 1 over density of solution 2 given my number, the equation number 1. Right? So I would cancel out, divide by gravity, gets canceled out, and then divide by A plus B, and then divide by density of solution 2 to both sides. When I say divide, I mean divide to both sides. Okay? So you end up with what I have here. Right? Density of solution 1 to density of solution 2 is equal to B over A plus B. I'm literally doing algebra to get that from equation 1. So isolate for density of solution 1 divided by density of solution 2, because that's what gives us a ratio. So ratios are what? Division, right? In fact, other countries teach division and they call it ratios. In England and in Singapore and in Malaysia, they teach, because they're all on the British system, and same thing in Australia, they teach division as ratios. We actually call it divisions. Someone asked, but how do you know they aren't equal? Sure. Okay, one question at a time. To answer that last question, because Michaela was saying that why is density 1 using A plus B and density 2 using only B? Because if we look at this line, everything above here, the weight of this fluid is going to be equal to the weight of that fluid. That's why. Does that make sense? Yeah, it's just weight, right? We're looking at the weight of fluid. Since the fluids have different densities, they need to have multiple different volumes, right? Because weight is what? mg, but density times volume is equal to your mass. Correct. Because how do you find volume, right? Volume is cross-sectional area times height. So if I plug it in, mass is equal to density times cross-sectional area times height. Right? I just canceled out the cross-sectional areas. Increase A. Are you talking about A as in cross-sectional area? Yes, increase height, because it has less volume, right? Look, if we're comparing it, this amount of weight pushing down from that liquid is equal to this amount of weight pushing down from that green part of that liquid. We're just measuring the balance of weight, right? Because what is pressure? Weight per cross-sectional area. Does that make sense? And that shows that, look, if I require more height or volume, that means that my liquid is less dense. Okay, so someone's wondering how I can compare densities. So you have to understand that this equation is true, right? Can we say that equation 1 that I've written here, that I'm going to star, is true? Good. So we know that that's true, right? Because of the weight. The weight on the left is equal to the weight on the right. We're good there. So if we're comparing ratio of densities, what am I going to do? So let's start with that. We have density of solution 1 times gravity times A plus B is equal to density of solution 2 times gravity times B. Now it's just algebraic manipulation, right? To find the ratio of densities, it's literally one density divided by the other. So if I divide everything by G on both sides, what happens? They all go away. If I divide everything by density of solution 2 on both sides, I'll end up with B on this side, right? And then if I want to find the ratio of density of solution 2 to density of solution 1 by itself, I'm just going to divide by A plus B, that height. Why D is true? Yeah, people are still confused. Someone is asking me to explain why D is true. Well, some people are still confused by why C is false. So we want to make sure that's true. Everyone's on the same page first before we move on. It's okay. Like it's raining. It's Monday too. Like I always teach physics on Mondays just because that's generally like when I have free time. But yeah, Mondays are like the worst. This statement is saying that the density of solution 1 to solution 2 is A to B. That's what statement C is saying. In words, I'm just translating it to an equation for you. The ratio of density of solution 1 to solution 2 is the ratio of A to B. What does it mean to be a ratio? It means to divide, right? So get used to seeing that because they love using ratios on the MCAT. And then we can clearly see that C is not the same as this is what we solve for. So hence why C is false. Cool? We're good now for everyone. Did I answer all those questions? Sorry, there was a lot that came in, and I want to make sure I answer everyone's questions. If I miss you, I apologize. Good? Okay. So let's explain D, because there was another statement to explain D. So the relative densities could not be determined if one of the sides were closed. So imagine if I put a stopper on one side of this tube. So let's say I put a stopper here. So one of these sides were closed. So how does equation 1 change? What does equation 1 lose? No atmospheric, because there's no pressure due to atmospheric pressure pushing down, right? Plus, we don't even know what the pressure that these molecules are getting, right? We have to have a gauge here to measure that pressure on there that those molecules are getting compressed against that stopper, right? Because it's eating some of the distance in section A, right? That would have made it balanced. So now we have that, right? Plus this unknown gauge pressure that we would have to measure, right? And since that's the case, we can't simply cancel out atmospheric pressure, and we have this unknown pressure there of those molecules getting pushed against the stopper. So we can't find a ratio of density of solution 1 to solution 2 like before in part C. This is why this is a true statement. then you would have what the right side of the equation says. Someone asked, what if it stopped on the right side and air is trapped on top of solution 2? Then we assume that the air that was in there would be equivalent to what atmospheric pressure is at that given point, right? The relative density of molecules in the air or gas at that point that's pushing down is equivalent to the atmospheric pressure at that point pushing down, plus the hydrostatic pressure that we have. Yes, no air, no ATM. Right? No column of gas above you. That's what the last one was talking about, right? The first thing that we talked about. So if there's no gas above you, don't we lose P1? Doesn't P1 go away? In this equation right here. So all you're left with is just your hydrostatic pressure, rho GH. Does that make sense? Excellent. Cool. So these are the type of questions that you'll see on your MCAT, right, with regards to understanding hydrostatics. The next question, actually, the next topic that we have to go over is called Archimedes' principle. The third situation where you have fluid statics. Archimedes' principle. Not S dot, it's just, this is the whole principle where he discovered the whole story with the crown, and he discovered that the crown wasn't made of pure gold. Subsequently, the crown maker lost his head, but they gloss over that point. But yeah, and this is also the one where he runs around naked after taking a bath and he yells "Eureka, Eureka," which means he found it, because he was tasked with determining if a crown was made purely of all gold, or did the jeweler use an alloy. Well, I guess I'm going to tell the story. And so he was sitting in his bathtub and he didn't figure it out until he realized that the weight of an object, because we know the density of like gold versus the density of like lead or other metals at the time, or the precious metals at the time. And he found that the density, when compared, is relative, the weight of the object, the weight of the crown in this case, is relative to the amount of metal that was used, or the weight of the metal should be equivalent to the amount of fluid displaced that you have in your system, right? And the amount of fluid displaced is what he ends up finding out to be called buoyant force. Yeah, I mean, if you think about it, when do you have the best revelations, Charu? And you're blocked. Like, just imagine you're working on a research project, right? He was blocked, right? He couldn't come up with how to determine that this was made from real gold or pure gold. Like, he would have to melt the crown down, and then that defeats the purpose. The king would probably be really mad at him, probably chop off his head, right? So he has to do it without melting down the actual substance and then try to figure it out. So this is how he figured it out. You got to remember, primitive times, they don't have readily available electron scanning microscopes to determine the substructure of gold versus the substructure of lead versus the substructure of silver for you. We are so spoiled nowadays, right? We have all this technology. Yep, archaic times, archaic solutions. But you think about it, like, my best epiphanies that I've had for all research projects that I've worked on, and like my greatest ideas for like inventions and creations, it actually happened in my dreams, or when I was taking a shower and like, something was like, hitting my sensory, and then it was like setting off another part of my brain, and then like the connections happened, Now that's TMI. Oh. Well, I guess it isn't you, so it's okay. But yeah, we have no idea who your friend is too. Commoner. Yes, fun facts. But yes, if you think about it, most like most revelations happen because something else happens, right? But it's also good to know where it happens, because you think about it, these are just normal people, right? You put them on pedestals like Einstein's this genius, right? And he couldn't put his pants on, like half the time. So yeah, he liked to be a patent clerk for a reason. Yeah. Anyway, your professors are the same too. Shocker. But yeah, they might be like really geniuses in the field that they're in, but like they have problems just like everyone else, right? So just just keep it real for everyone, that like all these geniuses, all these forefathers that we think of as like these great men, they did great things, but they also had issues, right? You think, Michael Jordan was a great basketball player, but Michael Jordan was a closet a gambling addict. Well, not even closet, everyone knows about it, right? So everyone has their flaws. No one's perfect. Everyone's human. So just keeping it real. So Archimedes principle. The buoyant force on an object in a fluid has the same magnitude as the weight of the displaced fluid. So this is the principle he came up after all of that. And all it's saying is that there's this upward force called buoyant force on an object when it's in a solution, and it's simply the weight of the fluid, so the mass of the fluid above you times gravity, or the density of the fluid times the volume of the displaced fluid, so he would catch that displaced fluid, right, and just weigh it to figure out what the buoyant force was on the object. So this is the Archimedes principle. And realistically, what is it saying? So let's imagine if we have an object that's in solution. Let's say this is the way I've drawn it. This looks like it's 50% submerged. There's a lot of questions on this. Yes. Especially when you think of like ice cubes floating in water, right? And the ice levels here on Earth, you can extrapolate it even to like different objects floating in other objects, and the relative like percentage submerged that you have. Yeah, because you think about it, what is phlebotomy? Phlebotomy is this. What we measure as fluid pressure and stuff, we're taking an object and we're measuring that height. Someone wrote, what does the F1 stand for? What F1? Fluid. No, this is FL. Sorry. Formula 1. No, this is fluid. Fluid mass, fluid density. Okay. My FLs are fluids. That'll be a totally different kind of buoyant force, right? Because you think about that Formula 1 like fuel that they use. I know they do. But what does it mean when they say you use the best kind? It just means what? More bonds to break, right? The more bond breakage that we have, the more energy we have, right, from our combustion engines. So the more bonds, or the more carbon bonds and hydrogen bonds that we're breaking, the best kind of fuel it is. It's generally pure, right? It's generally the fuel that we use in combustion, right? In our cars, we use octane. I believe they use a higher grade or pure octane, less impurities. But realistically, it's just from bonds breaking and bonds forming, right, to get that combustion engine firing. So let's say this something is object is, submerged. We know that there's a buoyant force that's pointing up. You know that the object has weight pointing down. So if something is floating, what we noticed is that the upward force minus the downward force is equal to 0, right? So we know that buoyant force is equal to mg. And we know buoyant force is density of the fluid medium times volume of the displaced fluid times gravity is equal to, this is for the object, right? Density of the object times volume of the object times gravity. So, but if it's 50% submerged, that means what? For the density of the volume of the fluid displaced, that's 50% of that volume of the object. And we also see gravity cancels out. I don't want to have to write it anymore. Times density of the fluid, density of the object, volume of the object. So we can cancel out volume of the object, and we can see that, I'm going to rewrite it then. I'm going to rewrite it up here. Density of the fluid times 0.5 volume of the object is equal to density of the object times volume of the object. Left-hand side, right-hand side. I just substituted for density of the fluid. Since it's 50% submerged, that means the 50% of that object, in this case, my basketball, because I love basketball, and it's basketball season, and the Warriors rock. Again, finally. And no, I'm not a bandwagon fan. I've been a Warrior fan since their Run TMC days and their Sleepy Floyd days. No, they're doing pretty well without Clay. Imagine how well they do with Clay. And you'll see that the ratio of the density of the object over the density of the fluid medium is equal to 0.5. So we can simply say that the percent submerged of an object is equal to the ratio of the densities of that object to the density of that fluid medium times 100%. So this is one of those equations that comes up quite often because they love asking about percentage submerged in solution. Another thing that they love to ask is what we call apparent weight. And realistically, apparent weight is, imagine if we had a scale here that we weighed that thing, and that's simply the normal force. So normal force is what we call apparent weight, okay, for that object. So that said, let's take a look at a question. Anything with regards to this? I just carried this all the way up here, and then this led me to this equation. Okay, that result. I'm just drawing arrows. Sorry, it was tight on room. And normal force is what we call apparent weight. Okay. Any questions before I move on and ask you some questions? Okay, so this type of question is usually an MCAT favorite. So 2. The density of ice, like an ice cube, is equal to 917 kilograms per cubic meter. And we know the density of water is 1,000 kilograms per cubic meter, right? So that we know it floats. So when a glass of water with an ice cube floating in it is transported from the Earth to the moon, the ice cube will do which of the following? A, float higher, because gravity is reduced. B, float lower, because gravity is reduced. C, remain the same, unaffected by changes in gravity. Or D, float higher because gravity is increased. Why C? Sophie, you were the first to answer.
Should I just unmute and say?
Yeah, it's much easier than just typing it out.
Yeah. Okay, so I thought it was C because when using like our equation, gravity cancels out on both sides.
Correct. So that means the gravitational constant acceleration has no play in both equations, even though they're defined as having it in both equations, right? The weight and the buoyant force equation.
Yeah.
Yeah. So just remember that when you're putting them together, gravity always ends up canceling out. So regardless of whatever gravity is, they love asking this question. And for the life of me, I've had really smart kids just totally forget that. Like, and it's really easy right now because you think of it, oh, he just went over the topic. Let me ask this question. This was an impact question. And a student came back and told me, so they changed it. So instead of having the ice cube in water, they had a hot air balloon that was here on Earth, and then they transported the hot air balloon. Given that the density of the air in Mars was the same as the density here on Earth, they just transported it, and then Mars has obviously a smaller gravitational constant acceleration than Earth, and they give you the different gravitational constant accelerations. They ask you, how would the hot air balloon, would it rise up, would it go down, would it stay the same? And they gave you the different reasons, right? And they were like, yeah. He's like, it has to go down, right? Because there's like less gravity. Less gravity means less buoyant force, so that means the weight should be coming into play. But I was like, they both affected by gravity the same way? Then he thought about it and he was like, no. This question. Literally. Okay. So it's one of those independent things that they love asking all the time because it really does give you a reality check. Correct. It's always related to the ratio of the densities of the object, right? That's why when you guys did your things floating, like remember in high school when you guys did like a Cartesian diver and stuff like that, when you squeeze on the bottle, i.e. increase the pressure, increase the density of the fluid, what happened? the thing began to sink, right? And then you let it go, the diver began to float up again, right? Because the ratio of the densities weren't off. So if you think about it, let's go back. Actually, we don't have room. But the density, so the ratio of the density of the object to the density of the fluid medium, if it is less than 1, then the object floats, right? If that density ratio is equal to 1, object is submerged 100% in water or in fluid at the surface. And ratio density of the object to density of fluid medium is greater than 1. Obviously, the object sinks. Okay? And that's just simply just that ratio to determine whether something floats in another medium, right? We're just comparing relative ratio of densities. If the surrounding thing is more dense than the thing on the top, then the thing on the top will stay above it. If the thing on the top or the object is more dense than the surrounding medium, then it's going to pass through that medium, right? Because it's not as dense and go to the bottom. Does that make sense? Archimedes principle. Correct. Ratio of densities, or whether something floats or sinks in any medium, is simply the ratio of the density of that object to the density of the medium that you're in. Okay, so just keep that in mind because they love asking those types of questions on the MCAT. Another question that they like to ask, sorry, I want to clear this. We're good? Okay. Another question that they like to ask, looks like they don't give you enough information, but I like this type of question. Get you guys thinking. Here you have to actually do some calculations. So, third question of the day. We know that an object weighing 96 newtons is suspended by a string while completely immersed in water. The object has a density 3 times the density of water. I want to know what is its apparent weight in this solution. So be able to draw yourself the picture of what's happening. We have an object that's suspended by a string that's underneath water. Okay. Find me the apparent weight. Answer choices are as follows: 64 newtons, 48 newtons, 32 newtons, or D, 24 newtons. Another way of asking this question would be, what's the tension in the rope? literally means the same thing. What is the apparent weight? What is the tension in the rope? This one I want you guys to sit down, think about, build those neural connections and pathways to solve this. It's just forces. So what are the forces acting on this object? Yep. And the thing we're trying to find, the apparent weight or the tension. So we'll say tension, we'll say F buoyant, and the weight. You already know the weight of the object. It's given to you. It's 96 newtons. Yeah, it's 96 newtons. Apologies for my writing again. An object weighing 96 newtons is suspended by a string while completely immersed in water. The object has a density three times the density of water. What is its apparent weight? So we also know that the density of the object is equal to 3 times the density of water. Realize we're just doing summation of forces here. The only thing we're trying to figure out is the difference between them. We have this new thing called buoyant force that we have to take into account. So some of you have come up with the correct answers, others are still working on it. 3. Wow, the 3 can't be that bad. Sorry. So its density of the object is equal to 3 times the density of water. I'm just translating what it said in sentence form into an equation. The object has a density 3 times the density of water. So that's what it looks like in equation form. Okay, so let's do our forces. So we have tension plus the buoyant force minus mg is equal to 0, right? Staying still, static. So therefore, to find the apparent weight, we need to find the tension, which is simply mg minus the buoyant force. So if we write it out, mg is simply the density of the object times volume of the object times gravity, minus buoyant force, which is density of the fluid medium, in this case, density of water, times the volume of the object, because that's how much volume of fluid was displaced, times gravity. But we know the density of water is simply 1/3 the density of the object. So we see that this is 2/3 the density of the object, volume of the object times gravity. But we know what that's equal to. That's 96 newtons. So 96 divided by 3 is 32. 32 multiplied by 2 is 64. Any questions on that? Density is volume of object. The volume of displaced fluid is the volume of the object because the volume of the object is 100% submerged in water. It happens. It happens to the best of us. Sorry, I was reading a comment and responding back to it. Any questions on this? So you see that we're still using forces, except now we have included liquids into our forces. So like I said, book 1 is like all the mechanics that we did, from kinematics to forces to work and energy to torque to periodic motion and waves. All of that is what we consider mechanics. We're going to apply all those mechanical things into things that typically you don't think of as mechanics, like fluids. Okay, so this is one way we're going to look at that force balance that we were talking about all the way back then. Unfortunately, no. If you try to do this intuitively, you can go horribly, horribly wrong. Yeah, you would have to look at each component and see where each thing was. Like, even I don't feel like confident to do this intuitively, where it's like, oh, 96, I should be like 2/3 of that. Why? Yeah. Sorry. Yeah, timing usually in the fluid section with fluid application and fluid dynamics is generally pretty hard. It's a lot of mathematical calculations and manipulations. This is why we practice all that stuff earlier with kinematics so that we can get comfortable with doing a lot of like arithmetic and math so that we can do that. Do we get thin tip expo markers. I believe they only supply you with sheets of scratch paper at the test site. Uh, you're allowed to do scratch work with a pencil and scratch paper. I don't know if they allow you to have a white erase board or anything that you bring in separately besides a number 2 pencil or something to write with, and that scratch paper at the Thompson Prometric Centers. So, I substitute in. But it's generally you can bring in your writing utensil. I don't think they're gonna like check your writing utensil. Density of water, so I divide by 3 to both sides, is equal to 1/3 the density of the object, right? And then I substitute that in right here for this. Oh. Okay. So to go from here, I just substitute in, I just did algebra and added mg and subtract buoyant force. Subtract buoyant force. That's why it's mg minus buoyant force to that side. Oh, they check your glasses because of Google Glass and recording devices in glasses now. They will check your glasses. Yeah, they're because technology can be used and it's readily available to the common, wealthy person, and to the common masses because of Google Glass. They don't want you recording any of their actual test questions and transmitting it to students that might be taking it later in that day. Yeah, they will check them. It's just being thorough because um they had this happen for an MCAT sitting where when Google Glass first came out, they didn't check glasses. People that took it in Singapore relayed their whole tests, and so everyone that took it after that like had a preview of every test question. And you know American kids, we didn't take it until like 14 hours later. Like they had basically the whole test, like they knew what the questions were, what the passages were. It was a huge unfair disadvantage. Oh, so what is mass of an object? Mass is just density times volume, right? And buoyant force is density of the liquid times volume of the fluid displaced times gravity. And I just substitute in volume of the fluid. Since it's 100% submerged in solution, it's the volume of the object. I think I explained it in words. I didn't like write it out. But yes, think about it. Imagine you, and it was so bad. Hair clips are pen drives. You have flash drives that you can have like stored like test information that someone could have like digitally sent you. That's why hair clips are excluded. People are creative. Yep, it's crazy. And all you have to do is just like put it into any of the USB ports that like they have at the computer, right? And it'll just come up. Like you can actually literally like copy like like you can dual screen. They have to be. People have found ways to cheat. I believe you can carry a backpack in. They will check what's in the backpack, but you're not allowed to keep it on the table. So it stays under your seats, and it's regimented. And then the people, oh no, but no backpacks now either. Wow, that's crazy. So basically, if you want to like bring test things to like quiz yourself in between breaks, you can't even do that. Wow, that's crazy. That's nuts. I was like, I wanted to bring like, like just imagine like you had like some Berkeley Review like workbooks you wanted to do some questions on just to like or do some reading. Can't even do that. Wow. That's crazy. Yeah, I think it's just because it's so easy to cheat now. You better be able to bring food because you're gonna be there for like 8 hours, 9 hours. You're gonna faint from like oh jeez. Yeah, is it a palm scan now? It's not a thumbprint anymore. To make sure that like people aren't walking in as you. Like Coney Wynn can't come in as Jonathan Tang. If I had a dime for every time someone asked me that question, Jonathan, I would be richer than Warren Buffett. To be fair, I can guarantee you are probably a perfect in the physical sciences, biological sciences, cars, sociology. I don't know. I'm pretty sure I could like honestly like a grown adult should be able to take this test and like do super well. Kind of like you guys taking SAT and be able to like crush it. So all right. That's fluid statics. We have to still do fluid dynamics. So let's make sure we get through that in a timely manner as well. Yes, let's go. Let's do this. So fluid dynamics. This is fluids in motion. So there's real world fluidics and then there is ideal fluidics. So we'll deal with the real world first. So real world fluidics, we're talking about viscous. Apologies. I changed it. It clearly said 96 and someone commented on that. Sorry. So real world fluidics. We're talking about viscous fluid flow. What is viscous fluid flow? So viscous fluid flow entails anything that has what we call viscosity, which is simply denoted by the Greek letter eta, which looks like an N with a curly. Correct. So viscous fluid flow is anything that isn't like, super smooth, like laminar flow or idealized flow. So this is anytime you have viscosity, you have fluid friction. And what that entails is, let's look at the velocity profile of viscous fluid flow. So what ends up happening, so this is your fluidic channel. Viscous fluid flow will look something like this. It looks like a nice little parabola where velocity vectors are the greatest in the center of the fluidic channel, and it gets less and less at the edges. The reason being, as molecules collide with the side walls, they come to a complete stop. So if you imagine, think of like this fluidic channel as lanes on your freeway, right? So every time there's an accident that happens, what happens? Dead standstill, gridlock, right? So the only places where accidents can happen are on the side walls of your fluidic channel, right? And that's what we call the viscous part of fluid friction, right? So molecules will collide with the side walls and create fluid friction, getting them to come to a complete stop, okay? The equation that governs viscous fluid flow is called Poiseuille's principle. He's French. It's undernoted Poiseuille's principle, right? Sounds like Poiseuille's if you're trying to spell it, right? We want to butcher it with the American pronunciation. Yes, it's pronounced Poiseuille's principle. Yes, I used to call it Poselli's principle, and then I took French, and then I was like, oh wow, I've been butchering this man's name for like years, teaching it. Babble. So Poiseuille's principle simply states that the volume flow rate of any fluid, and if you take in your heart and lungs lecture already, you guys call this blood flow rate, right? So it's simply the change in pressure times pi times r to the fourth divided by 8 times the viscosity times the channel length. So this is the unit. This is the equation for Poiseuille's principle. It tells you how much volume flow. So how much volume? So cubic meters per second. Cubic meters of the fluid going across that cross section per second. So if this was your fluidic channel, think of it as like a tube or a cylinder. Could be an artery, could be a vein, could be an arterial, whatever you want to call it, right? It's just some fluidic channel in which liquid is moving through. So pressure is the difference before and after a section of that fluid. R is the radius of that fluidic channel. Eta is the fluid that you're using. For us, it's blood, right? And blood or plasma, and then all of its particulate, what we call blood, right? Plasma is the purest form of the liquid in greatest concentration, right? And the rest of it, like red blood cells, white blood cells, like macrophages, all that stuff, those are all particulates, right, that are in the blood. So this has to deal with all those things lead to the fluid friction. Oh, yes, the SI units for viscosity. That's a good question. Thank you. Viscosity is Newton seconds per meters squared. That's the units for viscosity. And L is the length of your fluidic channel. This N. That's what it is. It's viscosity. So each type of fluid has what we call fluid friction associated with it based on the particulates that it has inside. And you'll be given the viscosity of those things in order to do this. Most of the time, they like doing the idealized equation, but for real world fluidic flow, we got to use Poiseuille's principle correctly, okay? So with fluid flow, you can have this viscous velocity profile if it's nice, straight, and streamlined, right? But there's such a thing as what we call random chaotic flow too, which we call turbulence, right? In order to know that, we need to know this number called Reynolds number. Reynolds number is one of 106 dimensionless numbers that scientists and engineers love to use. Why? Because we hate units just like you guys. Yes. It's very interesting to find out how much in common you have with your professors when you actually sit down and talk to them like people. And I was like, oh man, that's scary. I too will be you one day, fat, old, and very knowledgeable. But yes, Reynolds number. So Reynolds number tells us it's just a number, 2 times the density, times the velocity, times the radius, divided by the viscosity. Okay? What does that number tell us? When Reynolds number is less than 2000, we have what we call laminar flow. When Reynolds number is greater than 3000, we end up with turbulent flow. Density. What is after the 2? That's density. So the density of your solution or blood, right, the speed at which it's traveling, depending on if you're in your aorta, your arteries, your arterioles, your capillaries, the speed will change, right? And then the radius of those cross sections. So this is where all that stuff becomes applicable. And remember, this is all caused by what? Pressure, right? Force per cross sectional area that we talked about in terms of differences in between. Okay. So let's take a look at what is laminar flow and what is turbulent flow. But before that, when the Reynolds number is between 3,000 and 2,000, this is what we term the unstable region. Within the unstable region, you can have a variance between laminar flow and turbulent flow changing at any given point in time. It's no clear distinction. Imagine it being like, in the financial district in SF on a windy day, or, in Manhattan in the financial sector on a windy day, right? Some parts of it will be really windy, and then other parts will be calm and steady, right? Blood pressure. Blood pressure is how much force per cross-sectional area that you're getting. So this is telling you how much volume that we have going across. And if we take that, pressure is simply just the force that we have per cross-sectional area of what you're looking at. So, and then they talk about the mean arterial pressure. They're talking about the pressure over the whole cross-sectional area of all your arteries together, or all your arterioles together, or all your capillaries together. Correct. You get it all the time, right? You guys call it an arrhythmia, right? Uneven pressure in the heart, uneven pressure in your arteries and arterioles. You guys. Yes, I say you guys because you guys want to be doctors. I don't want to be a doctor anymore. Right? So I used to want to be a doctor. But yes, I commend you guys. Super noble profession to go into. I just found that like medical research and medical science, it just takes too long. Engineering, so much faster to get things done and get approved and have a project go from beginning to completion, right? Think of like a drug and drug development, right? That takes years, human trial errors, testing, going through that before you get like a drug from like start to completion. Think of like a procedure, right? Yeah, it takes like 10 to 15 years. Like no joke. FDA approval is so thorough. I went through the whole FDA approval process when we were designing medical devices, and I was working in medical device field, and I was just like, this is rough. You take it outside of the human and not having to do it, you put it in animals and other things, like testing is gonna be done in like maybe like a year and a half. But put it into humans, it's like we got to be safe about it. We got to have done trials, we got to have done tests, we got to make sure that those trials are safe. It has to be approved first before you can even run the trials. Like, yeah, that's why drugs cost so much money. Like, like the stuff that Bayer and Pfizer and Moderna and all those companies use. The reason like vaccines aren't made because they're not profitable. People just pay the bare minimum for vaccines, right? But like opioids and painkillers, they're super profitable, right? Because they made you addicted to them. They built that in. Those pharmaceutical companies know that too. I'm surprised they're not getting sued more. Anyway, Reynolds number. Let's get back to fluids and fluid flow, right? So if we think about what is laminar flow is what we consider streamline flow. So everything is nice and straight. So this is your fluidic channel. Everything is nice and straight. And if you think about it, what happens? The reason we get laminar flow is when Reynolds number is really low, right? And in terms of, blood, density, velocity, and viscosity, those are pretty much constant. They don't vary all that much, right? But what varies a lot in the human body? The radius, right? Going from your aorta to your capillaries, right? Which is like next to nothingly small, right? So what's happening is the reason it's laminar because you're getting one red blood cell that's going through at a different at the same interval, right? Think of like your capillary exchange is like one blood cell, red blood cell that's carrying like oxygen and transferring oxygen and carbon dioxide out between your myoglobin and your hemoglobins that are available, right? During your capillary. So that's why laminar flow is very streamlined. It's very orderly. It's one cell after the other because those radii that we look at are so small, right? The other case is turbulent flow. Turbulent flow, as the name suggests, is what we call chaotic flow. And actually, in order to do it, you actually have to use chaos math, or what we call stochastic math, which is white noise math, right? And you have to figure out randomly where molecules are going to be able to move. So if we're looking at one molecule moving across, it could be like this. That's one motion of one object or one particle moving across. And imagine there's a bunch of particles. What's going to happen? They're all going to collide with each other, right? That's why when your plane runs into turbulence, it doesn't create that lift that we expect for the plane, right? Because all these molecules start randomly hitting the wings, right? That's why your plane begins to vibrate. That's why your plane begins then to fall, because of the non-streamlined nature of that plane, right? Turbulent flow in real life, if you guys have ever gone water rafting, this is the white water part, right? This is class 3, class 4, class 5 rapids going on because all the molecules are moving every which way and they're colliding with each other, creating those air bubbles, which is why it's white, right? Laminar flow is those class 1, class 2 rapids, right? These are your church retreats when they take you on, like, let's go on a white water or a river rafting trip, right? It's so boring. You need to take water guns with you to make it exciting, right? Those are your church retreat ones, right? Class 1, class 2, that's your laminar flow, right? No white water, right? Everything is nice and streamlined, nice and steady. If your boat doesn't have a hole in it, you're not going to have much of an adventure on that trip. But yeah, super safe. Streamlined flow versus turbulent or chaotic flow. So that's the two differences in between, right? And if you think about it, during your diastolic phase, when you have your volumetric filling, it's done laminarly. And during your systolic phase, when you're shunting blood out of your left ventricle through your aorta, right? That's turbulence, right? There's a lot of pressure going through that aortic arch. Someone mentioned that they were talking about going through the Champagne Rapids in Jackson Hole, Wyoming. And I was like, yeah, I've been water rafting like all over the United States. And yes, it is really cool. But yeah, the turbulence is the crashing of all those liquid molecules with each other, capturing air, creating that white water, right? And so what we see as white water, like when we say white water rafting, it's totally thinking about all those liquid molecules going every which way, right? Some of them make cesspools, some of them make whirlpools, right? That could pull you down, right? Some of them go down and go over rocks, right? And go every which way. So, but the scary part about it is there's no streamlined nature to it. So you're basically, if you ever get under white water, you're getting tossed around. If you ever fallen off a raft, you feel it, right? You get tossed around like you're like, a beanbag or a pinball in a pinball machine, right? You feel this turbulence, right? So just be careful if you go into those like class 3, class 4. Like the only thing I haven't ridden, like I've done the Snake, the Columbia, the only thing I haven't ridden is the Colorado. I want to do the Grand Canyon one, but the wait list is like 7 months to a year. And they got longer during this whole pandemic because everyone wanted to do something to get out. But yeah, I was a very avid rafter for like many, many years, especially in my 20s. It was super fun, that and rock climbing. So one of those cool things that you do when you're young Too darn old for that now. I feel like I have more to lose. That's why I don't do it. Like when you're young and you're like, what do I have next to me in my name? Nothing. I don't have a house. I don't have like property. I don't have anything, right? It's like, yeah, go have fun. Not a big deal. Put my life at risk, right? Think about it. Yeah. Whitewater rafting is quite dangerous. Like, so with skydiving, riding a motorcycle, all those things that you did in your like early 20s. Hopefully you guys get all that adrenaline stuff out of the way before you become a doctor. Some doctors still do it to take off the edge because it's such a high stress job. But yeah. So difference between laminar flow, turbulent flow. So this is real world fluidics, okay? So now let's compare it to idealized fluidics. These are still fluids in motion. So let's compare it to idealized fluidics. So ideal fluid flow So with ideal fluid flow, we're talking about a non-viscous, so no fluid friction. Laminar is viscous, but since you're only getting, so someone asked, are laminar and turbulent flows viscous fluid flow? They are, but when you're getting the cross section down to be so small, the viscosity part of it narrows down because you're literally passing like one cell through at any given section. So that's why it behaves like laminar flow. Does that make sense? So there's less chances of you colliding, those molecules colliding with the side walls, because the molecules is the diameter of that side wall or that fluidic channel. Does that make sense? Cool. That's why it's so streamlined when you get smaller, right? Due to that Reynolds number relationship. So yes, they're viscous fluid flow. Laminar and turbulent flow. Except turbulence added a whole another layer of stuff that you have to deal with. The randomness of the molecules at any given point before they even hit the side walls. So non-viscous, no turbulence, and fluids are incompressible. So they behave like a solid. So you felt it, right? If you ever gotten hit by a wave on the ocean, like, and you got it blindsided you and hit you, it's like someone just basically pushed you, right? It's a huge wave of mass coming in and just pushing you, right? You see it all the time. Like you think about like what tsunamis do, right? They literally move cars, move houses, move everything, right? It's just a wave of mass pushing you. So real like ideal fluidics, we consider that the liquids are incompressible, so they behave like a solid. It's like if something collided with you, like a linebacker. Very similar, like getting hit by a linebacker blindside when you're a receiver is the same thing as like that feeling that you have when you have a wave crush on you. So very similar. So that's why I mean when they like behave like a solid. So the first thing we need to know about ideal fluid flow is the law of continuity. So the law of continuity simply states that the volume flow rate is always constant. So as we go and shrink down to smaller cross sections, the volume flow rate at this cross section is going to equal to the volume flow rate at this cross section. We'll call this A1, we'll call this A2, we'll call this V1, we'll call this V2. So volume flow rate, Q, is equal to the cross section times the velocity, which is what? Cubic meters per second is constant. So with that relationship, we know that A1 V1 is equal to A2 V2 at any given point. Okay. So we want to find the velocity of one thing. We just simply take the ratio of the areas across it. So no matter where we're going, the amount of volume flow rate that we have going across, if the arteries or get smaller or the radii get smaller, going from like arteries to arterioles to to capillaries, so to speak, right? The same amount of volume is going across there at any given point in time, which just means what? It goes faster. You've seen this in real life, right? When you were like 7 or 8 or like hitting puberty and you wanted like you had chores to do for your parents, they always ask you to water the lawn, right? And if your parents didn't have a nozzle on, like you were poor, you only had a hose, what did you do, right? Instead of dragging the hose everywhere, because that's tiring, what did you do? You put your finger over the hose. And what did you do? Notice the smaller cross section that you had in the hose, the faster the velocity was that came out, right? So that's why you were able to stand and not have to move the hose, right? Because it shot the water further. So that's what basically a nozzle does, right? It puts a lot of the things. Sorry, what's in parentheses? Meters cubed per second. That's the units. So it's the same units as volume flow rate from Poiseuille's principle, right? All it's saying is that volume flow rate is constant. That's what the law of continuity says. Does that make sense? Meters cubed per second. So the second thing that we need to know is Bernoulli's equation. But Bernoulli's equation is really energy conservation. So energy conservation, there's 3 energy conservations with Bernoulli's equation that you need to know. The first is the work term is conserved. And work is simply what? Change in pressure times volume. If you don't think that's work, what's pressure? Force per cross-sectional area. What's volume? Cross-sectional area times the height or length, right? Isn't that force times length? Isn't that work? Or force times displacement? The second thing, kinetic energy is conserved, right? So 1/2 mv squared. So we can change that into 1/2 times density times volume, capital V, times velocity squared. And third, we have our potential energy term, and that's conserved. Potential energy we know is mgh. That's density times volume times gravity times height. The reason I change everything into density times volume, right? With a liquid, we can't just take a chunk of water and go, let's weigh it, right? We can put it into a container. We know it has a certain volume. We multiply to that density, and then we can actually weigh it or get the mass. Okay? So it's always density times volume for all fluid equations. For kinetic energy, is the last thing written R or V? It's V. Little velocity. See, it's this V right here. Same V. Okay? This just happens to be the mass right there. Density times volume. Okay? So, Bernoulli's equation is simply energy per unit volume is constant. Right? Because we know the law of continuity exists, that's what Bernoulli was using. He says that it's the same volume at any given place that I go across, right? At every cross section. So I can conserve all the energies that we have here with volume involved in them, right? And just cancel it out. So that's why you end up with pressure, which is the work term, plus 1/2 rho V squared, which is the kinetic energy term without volume, plus Sorry. Apple Pencil just ran out of juice. Give me like 10 seconds. But you can see that if we divide out the volume, you'll end up with rho GH for your potential energy term in your system. And all of that is always constant. So we get a lot of comparison questions where we go P1 plus 1/2 rho V1 squared plus rho GH1 is equal to pressure at the second point, at some point further down the fluidic channel, plus 1/2 rho V2 squared plus rho GH2, given the different velocity, different height in the fluidic channel. Remember, height is always measured from the ground because it's potential energy. So it's relatively how high you're moving up or down, right? And this is Bernoulli's equation. Energy conservation, given the fact that we know that the volume is always constant for an idealized fluid, okay? So with that, you get a bunch of relationships comparing fluidic flow from across one section versus another section, right? So let's look at the airflow across a wing. So if we think about it, if we look at the cross section of an airplane wing, it actually looks something like this. It's much flatter, but you can see that this side is big and this side is narrow. So as air molecules move across it, you think about the top, this is a much larger distance than the bottom, right? In terms of distance. So D top is greater than D bottom, right? But the air molecules move it in the same amount of time. So we know that the speed at the top for the air molecules is greater than the speed at the bottom, or the velocity at the bottom. They're roughly the same height, right, in terms of potential energy. So if we're comparing Bernoulli's equation, we see that pressure on the top plus 1/2 rho V top squared is equal to pressure on the bottom plus 1/2 rho V bottom squared. So we know the top velocity at the top is greater, right? That means the overall kinetic energy term is greater, which means there's less pressure at the top. And if the molecules at the bottom are moving slower, has less kinetic energy, that means the total energy had to go into the work that's being done by those air molecules as they hit the underside of the wing, right? So increased pressure on the bottom. So pressure on the bottom versus pressure on the top is greater, right? If pressure on the bottom is greater than pressure on the top, there's a pressure difference, and that creates a force. And that force is what we call lift force, to lift the airplane wing up. So when air molecules aren't laminar, right, air isn't going above the airplane wing faster than the air molecules on the bottom, they're randomly colliding into them because of due to turbulence, then you'd lose that lift force. That's why your plane tends to drop out a little bit when you run into bits of turbulence. And then if your pilot's not good and he didn't overcompensate with increased thrusters and using up more gas for your turbines, then you can possibly drop if they're just gliding along. Okay? This is how you would use your Bernoulli's equation. Okay? With that said, we are completely finished with fluid statics and fluid dynamics. If you have questions, I will be here for the next hour and I can answer anything. We had a student ask to do example 5.2a. I can work through that now and we can start from there. And then if you have questions, feel free to stay. Otherwise, we're done with fluid statics and fluid dynamics. Feel free to ask any questions otherwise. But I'll see you guys on Wednesday, and we'll finish up the acid-base lecture and go into buffered titrations. Okay? Thank you so much, guys. Oh,